ideally, if you're not getting the stuff, you should meet with me before the quiz instead of having to meet with me after. I'll be here on Wednesday super late. I'll also be here today super late. And Thursday and Friday. You should show up. So, here we are. We're on page 10. So just reviewing perpendicular bisector theorem. Yes, Ellie. Yes. What time? Yeah, I'll stay. Let me write a note. It is Super Tuesday today, so you will be taking me away from that. That's all right. I'll turn on a straight. I need to stay late on Wednesday and Tuesday.
I know, it's because I have a whole full bag now.
Cool. I got new pens. I got some more pens for you guys. $26 means 2 of every color. So that's added on. I took the best for myself since I need to use these for you guys. I also got a big buttload of black pens because I go through those super quickly. And black Sharpies. And got new erasers. Yeah, I know, right? All for my kids. Total of $80-some right there. It is expensive to do what I do. But I want to make sure you guys have the best of the best. That way you can do the best on your quizzes. Hopefully you're investing the same amount of effort as money as I am. All right, so here we go. So we know that perpendicular bisector theorem says that if you have a perpendicular bisector, why do we call it a perpendicular bisector? Because it's perpendicular and it bisects. So the perpendicular bisector of this segment is this guy, right? He perpendicularly bisects that segment. Any point on that segment will be the same distance from the endpoints of this segment, right? So any point on the perpendicular bisector, like this point right here, will be the same distance from the endpoints of the other segment, right? These are my endpoints on the segment. This will be the same.
What's that called?
What's what called?
Is there like a theorem?
Perpendicular bisector theorem.
Oh, that works for that?
Yep. So all of those will be the same distance from the endpoints, right? Now, they're different distances, right? This guy's further away. But the distance from this endpoint and that endpoint to this guy will be the same. Always, guaranteed. Same thing for this guy and that guy. And as you go further down this flagpole, essentially, you get to here, all the way at the bottom, right? And will this point be equidistant from the endpoints? Yeah, right? Look, it is, right? So the idea is that this holds as you go up perpendicularly from there. Yes?
But we can only do it if we already have the
Yeah, you got to know that it's perpendicular bisector, right?
Yeah.
Any point on the perpendicular bisector will be equidistant from the endpoints, right? So we proved that yesterday. We were given this, right? A perpendicular bisector. And we said, look, shared side, side angle side, triangles are congruent. And if the triangles are congruent, then by CCP, then these sides are congruent. So yeah, D is equidistant from A and C, right? So this is true for any point on a perpendicular bisector. Now that's really useful. Now, we've been able to do this before we had this theorem, right? We just did all this work to prove that those two sides are the same. Now, perpendicular bisector theorem, boom. How do you know that D is equidistant from A and C? By perpendicular bisector theorem. And it saves you all that work, right? Whenever you have something like this, you get the sides for free, which is useful because that means isosceles triangle, right? Super, super useful stuff. So we're going to mess around with that today. My advice to you is the same as always. It seems to me that my students do the best when they do not write but instead watch and pay 100% attention. For instance, Shelby told me I could say this. So Shelby, last hour, came in during second hour and learned all the stuff we've been doing last week and this week in about 10 minutes. And it's because she chose not to write stuff and just watch and observe. You came in last week and learned a ton of stuff that you were behind on just by watching. Look, you guys should be used to my system by now. And the reason I chose this system is because, especially for geometry, but true for everything, I think, but especially for geometry, the battle is seeing it. If you watch me draw this stuff in as I go, it makes more sense. If you look at it all at once, it's like, wait, what? And when you draw and you're like copying stuff down and then look up when it's done, you're essentially looking at the finished product. You're not seeing how I got there. So watch as things go.
Don't lose.
That's why I do it this way, right? I make it so you literally do not have to take notes. I've got a recording, I've got this, right? Whatever you need, it's for you. Because if you don't have to take notes, then you can watch, and that's really the best way to learn, especially for geometry.
We can't turn in a blank packet, right?
You cannot, but I can give you this at the end and give you time to write stuff down. I guarantee I could go a lot faster in class and not have to do so many breaks for you to copy stuff down if we just did it all at the end. I do that in my other classes. Third hour, take advantage of that. Okay? So as we go today, wait till the end and I'll give you time to write. I guarantee there will be less questions if I'm confused because you'll know what's going on. And so during that time, we'll copy stuff down. Okay. So, perpendicular bisector theorem. Any point on a perpendicular bisector is equidistant from the endpoints. Okay? We get these sides for free. Again, if this, then that. Any point on it. Today we're going to prove the converse of that, which says that if we know a point is equidistant from the endpoints, right? See how this point's the same distance from here and here, right? Then we know it must be on the perpendicular bisector. So if I've got this, then I know this. Then I know that that point must be on my perpendicular bisector. So again, watch as I go. I was given this, and because I know those two sides are congruent, by perpendicular bisector theorem converse, I know that that point must be on the perpendicular bisector. Now, we're allowed to drop a perpendicular whenever we want. We're allowed to put a midpoint whenever we want. And we're allowed to drop a line from a vertex whenever we want. But to do all three, from here at 90 to the midpoint, you can't just do that at will, right? If I've got a triangle like this, well, here's the midpoint probably, right? Right? 90 degrees. Can I say that's 90? Yes. No. I can't, right? I can't. There are some triangles where that won't be the case, where it won't be the perpendicular bisector, right? That's not true. You can get that, right? You can draw a midpoint and connect it up. That's fine. That's always legal. You can always drop a 90, right? But to do all of that at once, no way. You can even have a triangle and say that's the midpoint, and I'm going to go up from 90 from there. That's totally cool. You can do that whenever you want, right? But to have all three, where it's hitting the vertex, the midpoint, and is 90, you can't just do that at will, right? You can assume some of these, right? But you can't assume all of them. So just by knowing this, I know that not only is it on the perpendicular, I know it's also on the perpendicular bisector, right? All of that at once. That's a really powerful thing. It gets all three to line up. It essentially means, since we have an isosceles triangle, that if you go 90 straight down, it'll be the same as the perpendicular bisector, otherwise known as the orthogonal, right? The orthogonal will be the same as the perpendicular bisector. So if we get this, we get that. Okay? How are we going to prove that? Is this thing blurry? Keep turning around and it looks like it is. So we're going to start with this. And we're going to prove this, right? So we can assume some of these things. Let me show you what I mean. So first we need to create a line here so we have two triangles to talk about, right? So let's do that. So let there be a line. Let's call it line BD. Okay? Now you have a choice when doing this proof. You can say that line BD is 90 degrees, right? Or you can say it's connecting the midpoint to the vertex. That's fine. You can make that happen, right? You can draw that whenever you want, right? Pick a triangle, find its midpoint, draw a line. That's fine. Pick a triangle, draw a line, and say it's 90. That's fine. Some line on that triangle will be 90, right? You just can't assume both, okay? So for this one, I'm going to say let BD exist and let it be perpendicular to AC. And not only that, I'm going to say that ABC exists. Okay? So I'm just saying that, look, when I draw BD, I'm not just drawing BD over here, right? I'm drawing it so that it intersects AC. Does that make sense? Right? If they share a letter, that means they must intersect at B. Right? If I just said draw BD, you could draw a line over here and call it BD, right? I'm saying draw BD so that it's perpendicular and it intersects AC. Are we following on that? Okay, cool. So if it's perpendicular, then I get this, right? Cool. So I'm assuming that. That's totally fine, right? What we're going to do is prove that these two segments are congruent. And if they are, then it's a perpendicular bisector, right? So how do I prove these two congruent? Yeah.
I don't know the word for it, but since the lines are congruent, then
Yep.
they're equal distance apart. So it has to be because
So in proving the converse, we're not going to use the theorem. But good thought, yeah.
Use the isosceles triangle theorem to get the two angles A and C.
Right, so check it out. Isn't this a big isosceles triangle? Right? So by isosceles triangle theorem, we get these two angles. We know that angle DAB is congruent to angle DCB. Right? These two angles. You cool with that? Sorry that A and C dropped. I've fixed my Microsoft problems now. None of this saved after I made it. Okay, so we get these two angles by isosceles triangle theorem, right? We cool with that? Everybody cool up to there? Awesome. You guys are doing a good job today. So now, if I prove these two triangles congruent, then I can use CCP to get these sides, right? Do I have enough information to say these two triangles are congruent? How do I know they're congruent? Ooh. If I knew either of the sides, I could do that. You could do shared side and do HL, but I've already got enough. What can I do? Angle side.
I didn't. Wait, what was the rule for the right angle then?
HL you can do, but you need, hold on. You can do HL if you have the hypotenuse and a leg, but I don't have any legs. So Noah, I could get a leg by doing shared side here.
That's not what I'm confused about.
What's up?
I thought you couldn't use the right angle. That's for that's for two. Wait. All right, never mind. I don't know. I'm like.
No, take a second and ask your question.
it's only for two sides.
All right, hold on, Luke.
Can't say angle. Wait, what?
Oh, you can't say ass.
Yeah.
Ass doesn't work, right? AAS does, though.
Okay.
Okay, that's totally fine. So by angle side, we know that this triangle over here, I'm going to call it triangle ABD, just to try to keep it alphabetical, is congruent to the other triangle. Now when I match these up, A is going to go with C, B will go with itself, and D must go with D. So CBD. Nice. Nice.
Didn't we already prove that D is on the perpendicular bisector of AC?
Nope, because that's just the perpendicular, not the perpendicular bisector. Right? Right? So we're proving this theorem, right? That's what we're doing down here. So if these two triangles are congruent, these two sides must be congruent, right? AB is congruent to BC. So I know this to be true. And now, doesn't that make DB a perpendicular bisector? It does, right? We assumed the perpendicular part, and we proved it had to also be a perpendicular bisector, right? So, by definition, therefore, by definition, DB is the perpendicular bisector. This is my symbol for perpendicular bisector, right? Of AC. Right? It's the line that hits this AC at 90 and divides it in half, right? So it's a perpendicular bisector of AC. Now, how do we prove that D is on that? Well, isn't D one of the letters on my line segment, right? So therefore, D is on. You don't even need a reason. It's right there. Is on the perpendicular bisector of AC. And we're done.
So do we even have to write the last line? Or we just
I'll be picky. I think it's a free point, right? But you know when I set the bar low, they trip over it, right? So yes, I will require that last little bit. Okay? It doesn't even need a reason. I just need you to say it. So, I assumed a perpendicular line. That's fine, right? We can always find a perpendicular line on a triangle, right? And I said, have it intersect with AC. So then I said, because this is an isosceles triangle, those two angles are congruent by isosceles triangle theorem. Then by angle side, the triangles must be congruent, which means by CCP, these bottoms must be congruent. And if the bottoms are congruent, and it's 90 here, isn't DB a perpendicular bisector? Didn't I prove this? Yeah, I did. So DB is the perpendicular bisector of AC. And how do I know D's on it? Well, D is one of the letters, right? How do I know a point's on a line? Well, is that line written, you know, like, how do I know B is on this line? Because it's line ABC. B is on the name of the line, right? Yeah. Right?
You answered my question.
Okay, good. So I'm going to back up and go over it again, guys, right? I always do. Like a dead cat. During that time is the perfect time to write stuff down if you get it. And if you don't get it, that's the time to ask questions and pay attention again. Danny, yeah.
So by isosceles triangle theorem in blue,
Yeah, the blue angles, yeah.
could you say ADB is congruent to CDB?
Yeah, that's cool. Remember, wait, ADB.
Yeah, because angle A and angle C are the ones we got.
No, remember, if we're talking about an angle, the vertex of that angle has to be in the middle. ADB is this angle.
Oh, it has to be in the middle.
Yeah. See what I'm saying? Now, could you have called it angle A and angle C? Sure. There's only one angle A and angle C in this diagram. I just went for the three letters.
If we do that,
Chloe.
I'm just still confused on how if you put like DB, how would you automatically know that it's a right angle because you don't know.
Gotcha. So I assumed earlier on that DB is a right angle. And we're allowed to drop a perpendicular whenever we want, right? If I give you a random triangle, right, I can say from here, go down to the opposite side of 90. It's going to exist somewhere. So I said, let's make it happen, right? It should be there somewhere. Let's call it that, right? Then I prove that these are congruent. And so I prove that it's the perpendicular bisector, right? So I assumed one of them. You could have also done it this way, where you, let me get out of this crap here. You could have also said, look, every triangle, every side has a midpoint, right? And I'm allowed to connect dots. And then you could have proved that this was 90 and then 1, right? And the way you'd prove this is 90 is you'd prove that these two angles are equal after you get the triangles congruent, right? And if they're equal and a linear pair means they add up to 180, right? And if they're both the same angle, right, let's call them both x. They both have to add up to 180 by linear pair. What's x going to be? Not right, 90. Has to be, right? So you could have said, assume it's the midpoint and connect the dots. Assume it's 90 and then prove this, right? Either way, and then it's perpendicular bisector. Great question. Yes. Maybe fourth quarter will be the quarter where everybody gets it. Today is a good day. If you're still not getting it, it's okay. How do we feel? Questions about that? D's? I'll take D's for now. Okay? Gentlemen?
Makes more sense.
Daniel? I don't care whose phone it is. David? All right, so we're going to use this property, okay? Whenever we have perpendicular bisectors, we know that the distance from any point on that perpendicular bisector is the same to the side. So words are hard, math is easy. Essentially, whenever we have something like this, right, we know any point on here will be the same distance to the endpoints, right? We get that for free. And again, we could go through this whole process of proving that through getting the triangles congruent, blah, blah, blah. We're cutting to the chase. If you have this, then you get this automatically, okay? Automatically. Yeah?
Do you have a teal pen?
A teal pen? Yes, I do. It's like Danny throwing.
I've never done that.
All right. This is page 12.
Like I said, I throw it up and down.
So,
Are you doing something?
here's what we're done. Oh my God. All right, so here's what we're going to do. Okay? Our whole goal is to get this. Because if this is true, right, we draw a bunch of lines, and if we divide up the triangle into pieces, right, we go around the circle, A, B, C, D, E, F. If this is true, then by Ceva's theorem's converse, they must have all been intersecting at one point. They must be concurrent, right? So we're going to get this. The question is how. And how we're going to get it is using this thing.
What could be?
Okay?
Oh,
Yeah.
right there.
So we're going to divide up our triangle into all these pieces, right? And we're going to prove that the way we divided it must make them all equal 1. And if the way we divided it makes them all equal 1, then they must have all been intersecting. Okay? Again, words are hard, math is easy. Let me show you. So we're going to prove that the perpendicular bisectors of this triangle are concurrent. Cool. So let's draw in two perpendicular bisectors, right? Every triangle is going to have them, right? So remember, we're not allowed to draw from here to here, hit the midpoint, call it 90, and have it be congruent on both sides, right? We're not allowed to do that. That's too much. But I can say that it's 90 and midpoint. That's fine. So let me show you. I am allowed to do this. That looks like a midpoint. Let's call it D. And then draw 90 degrees from there, right? Because we're allowed to draw a 90-degree angle whenever we want. Notice I am not allowed to say that it connects to C, right? Because there are some cases, like this one, where it would not be 90, right? So I'm allowed to assume this. This is totally fine. The difference between last time and this time was last time we said it was 90, it bisects it, and it connects to C. We can't say all three, right? Pick two. Yeah.
So you can just draw that line?
Yeah. Think about it. Does every line have a middle?
Yeah.
Yeah, so why not let D be the middle, right? Could I find it if I measured? Sure, but I'm not going to, right? Let's just assume D is. Can't I draw a 90-degree angle with any other line, right? If I give you a line, can you draw a 90-degree angle with that? Sure. Right? What I can't do is draw a 90-degree angle, bisect it, and connect it to C, right? Because that's not always true. Like, for instance, if I did that, would that be 90? No way, right? But I can assume, look, every line has a middle. Let D be the middle, right? Every line, we can draw a 90-degree to it. Let's do that, right? That's totally fine. We just can't assume it connects to C, okay? So I'm going to draw it. So I'm going to say, let's have this be DE. I don't care where it hits on the opposite side. I don't really care about that much, okay? So DE. So let's have ADB exist and have it be perpendicular to DE. Okay? Let's do that. And actually, let's just let it be the perpendicular bisector of DE. Let's just do that. We'll go all out. I'll zoom in. That's my symbol for perpendicular bisector. Be cool with that? So let that happen. Then we're going to do the same thing for another side. This is going to get a little weird. So this looks like about the halfway point, right? Let's call it point F and let it be the midpoint, right? And I'm going to draw 90 degrees from there. So 90 degrees from there looks like about this. Notice I didn't assume it went through A. So I'm going to say let BFC exist, right? And let it be the perpendicular bisector of AF, more or less. Wait, not AF. FG. Okay, so I just drew another line. Notice that A isn't on that line, right? So it's FG. Cool. Now, these two lines are going to intersect at some point, right? They are. Let's call that point K. So the way we say that they intersect at K, we're going to say FKG DKE. Remember, if two lines share a letter, that means they intersect there, right? Okay. So that's just me setting up the problem. So we're going to prove that if I were to draw on the last perpendicular bisector, it would go through K. And if it goes through K, then they're concurrent, right? Right, they all go through one point. So here's what I'm going to do. Isn't K on this perpendicular bisector? Isn't K on this perpendicular bisector? It is, right? So by perpendicular bisector theorem, it should be the same distance to A and B. You digging? Right? Here's the segment. It's going to be the same distance from both sides, right? You cool with that? So from K to A should be the same distance from K to B. So I'm going to connect those up and draw them in. So by perpendicular bisector theorem, AK is congruent to BK. You cool with that? Right? It's on the flagpole. If I drew a point up here, it would be the same distance from here to here too, right? E is the same distance from A to B, right? Anything on that flagpole is going to be the same distance to the endpoints of that segment. Cool. Well, isn't K also on this perpendicular bisector? Right? It is, isn't it? So it should be the same distance to B, and it should be the same distance to C, right? Well, I already have the B to K done, right? So I know C to K is going to be the same. Right? Also by perpendicular bisector theorem. So I know that BK and CK are the same as well. Right? I don't know, I'll just throw it on there. You could write a whole different statement if you want. I'll just throw it on there. They're all congruent. So here's the deal. When I did that, didn't I also show that K is equidistant from both sides of this segment? Do you guys see the segment AC here? Right? K is equidistant from the endpoints AC, isn't it? Well, by the converse of perpendicular bisector theorem, right? If I have something like this, doesn't that mean that this point must be on this? Are you with me on that? Right? So I know that K is the same distance from C and A. So it must be on the perpendicular bisector of AC, right? So when I draw in the perpendicular bisector, it must go through K. So K must be on the perpendicular bisector because it's the same distance from both sides, right? Are you with me on that? This is the hard part. Are you seeing this? If you're not, it's okay.
Kind of.
Ellie? Sort of? K is the same distance from C and A, right? Well, if it's the same distance from two endpoints, then it must be on the perpendicular bisector, right? So same thing for this over here. If it's the same distance from C and A, it must be on the perpendicular bisector. So the perpendicular bisector of AC, the perpendicular bisector of BC, the perpendicular bisector of AB, they all intersect at K, don't they? We've proven that. So they're concurrent. So I know how I got that was I said, look, by perpendicular bisector theorem converse, K must be on the perpendicular bisector of AC. So whatever the line is that leaves AC at 90 and hits it in the middle, K must be on it, right? It has to be. That's the converse, right? That's when we said this. If you have this, then you must be this, right? That point must be on the perpendicular bisector. Well, we had this. We had it right here. So it must be on this guy's perpendicular bisector. So if K is on the perpendicular bisector of AC, and it's on the perpendicular bisector of FG, and it's on the perpendicular bisector of DE, then they're all concurrent, aren't they? K is on this guy, he's on this guy, and that guy. So they must all intersect at K. Therefore, perpendicular bisectors of triangle ABC are concurrent. And where are they concurrent at? K, right? I don't need to write that because that's not what they wanted. But they must all intersect at K. So while you're copying this down,
That's what they wanted.
I'll run through it one more time if you need to see it. Right? They intersect at some point, we'll call it K. If they intersect at a point, right? K must be the same distance from here to here as here to here. Because it's on the flagpole, right? You cool with that? Well, it's also on this flagpole.
But that's not in the middle, right?
I know, I drew it very, very sloppily.
Oh.
So it's also, if you look, on the flagpole of this side, right? The perpendicular bisector. So these are all the same distance. If it's the same distance here and here from these guys, then it must be on the flagpole of this side. It has to be. Are you starting to get it? I'll do it one more time. Okay? Two perpendicular bisectors. They intersect at some point. We're going to call it K. Well, if K is on the perpendicular bisector of this side, right, then it should be equidistant to the endpoints. Are we cool with that? Right. Well, look at this side. Isn't K also on the perpendicular bisector of this side? Then it must be equidistant from these endpoints, right? You cool? Right. Now, converse. If it's equidistant from the endpoints of a segment, right? If we have something like this, then we know this. Right? Isn't it the same distance from both of these endpoints? Well, that means it must be on the perpendicular bisector of this side. It must be, right? If we have two sides congruent, then we know it's on the perpendicular bisector. So where do they all intersect? K. So they're concurrent. I don't think this proof is technical and hard. The hard part about this is not the technicality, it's the seeing the picture, right? Chloe, do you feel like you see it sort of?
Yeah.
Okay, that last bit is the hardest to see, right? But that's the key, yeah.
So, the stuff we went over like last week.
Sure.
Are we gonna go over that again?
Yeah, we do a review day on Thursday. I'll try to start review early on Wednesday. I'll try. So, that's the idea. We assume two perpendicular bisectors intersect at K. And then we prove that the last one must also go through K, right? And we win. They're concurrent. We have so much time now. It's amazing. Let's look at 13. Actually, you know what? Before we go into this, do I want to back up and... We'll try it.
Can I trade you this one for the orange one?
Yeah. You can keep that one. Keep it for now.
Okay.
So, how do we prove orthogonals concurrent? Notice, I didn't teach you like an orthogonal theorem or anything before this, right? Before we proved angle bisectors concurrent, we learned angle bisector theorem of triangle, right? TAP, right? And before we did the perpendiculars, we did perpendiculars, right? And we learned the thing about perpendiculars, right? This guy. Medians, we didn't learn anything because they're all concurrent. They're all congruent and made it super easy. This guy, you don't need any special knowledge for except what we just did, okay? So here's what we're going to do, and this is kind of crazy. We're going to draw 3 parallel lines. I know. It's a beautiful proof. Are you ready for this?
Wait, why can't we do it the way we did the last one?
Well, this is orthogonals, right? That's different. We're proving that the heights of the triangle all intersect at one point, okay? Remember, an orthogonal is just a 90, right? It's not a perpendicular bisector. It's the perpendicular without the bisector, right? So here's what we're going to do. I'm going to draw a line parallel to AB. Let's call it, let's not call it anything yet. Let's just wait. I'm also going to draw another line that's parallel, not just to AB. I'm going to draw a line parallel to AC. Are you with me on that? I'm going to draw it right here. Cool. Lastly, I'm going to draw a line that's parallel to CB. And I'm going to draw it right here. It's parallel, trust me. So these guys are parallel. these guys are parallel, right? Single arrowhead. And the orange line is parallel to this guy. So I'm going to do double arrowhead here. Double arrowhead here.
So it's just same triangle.
Okay? Yeah.
Isn't that basically just making the same triangle but bigger?
It's making this the medial triangle. These are mid-segments, meaning that these are midpoints of the bigger triangle I just made. A, C, and B are midpoints of the big triangle. Right? You guys remember that, right? We had the midpoints and we proved them parallel and all that. Basically, I just did this problem in reverse, right? But if you don't see that, that's okay. So
I did it.
I'm going to say that I made a bunch of parallel lines. So let's call this D, E, and F. So here's what I'm going to write for that, okay? I'm going to say let DCE be parallel to AB, right? Those are my two blue guys, right? Let them be parallel. I'm going to say let FBE be parallel to AC. And I'm going to let DAF be parallel to CB. Okay? Now notice FBE and DCE both share letter E. That's because they intersect at E, right? The blue and the orange, right? So I wrote that. That's covered, right? And I did write that they intersect at D already because D and D, right? And I did write that they intersected at F already, F and F. So it's all taken care of. All that I just wrote by this. Create some parallel lines to these guys, right? And because they share letters, we know they have to intersect. Okay? Cool? So here's the thing. We're going to prove that triangle DFE, its perpendicular bisectors all intersect at one point, right? We know that to be true already. So I'm going to draw the perpendicular bisectors. So I'm going to let, hold on, do I need to prove this? Hold on. How much do I want to make you do? Okay. So if these two are parallel, we know that this angle and this angle are the same. Sorry, not this angle, this angle. My bad. This angle and this angle are the same. These two. Cool? You cool with that? Those two green ones that I colored in. We know a lot of congruent angles. So these two are congruent.
Wait,
We cool with that?
that's not CCP though, right? Wouldn't it be the one on the outside?
It's cap.
Oh. Well, wait, won't that still be the one on the outside of the green line?
Hold on.
Like,
We were going so well. My lines are not drawn very well, so I want to make sure that I'm reading this correctly. Hold on. You destroyed my brain. Hold on. These two lines parallel. This is the transversal. Yes, those are the same. Guys, two parallel lines, one transversal. These go together.
Oh, like, I think it was.
Two parallel lines. Orange is the transversal. They go together. It would help if I turned the diagram.
Would those be corresponding interior angles?
They're corresponding angles. Yep. Cap.
But I was looking at it like in a different way. Like, I don't know how to explain it. Like I was looking at it like it was what we first learned. Like.
Yeah, cap. Yep. Corresponding angles. Postulate. Yep. We have two parallels cut by a transversal, right? Those two are the same, right? We cool with that? All right. I also know, I want to stick with the orange theme, two parallels cut by this transversal means that this angle and this angle be the same. So these are both the same. Same thing here. These will be the same. Right? We've got a lot of congruent angles. I'm just showing you the ones that are congruent. You don't need to write this down. Okay? This angle right here, 2 parallels cut by a transversal. This angle and this angle will be the same. 2 parallels cut by a transversal. This one will be the same. 2 parallels cut by a transversal. These two will be the same. This will be the same as that. Once you see the pattern, you'll be good to go. Are we seeing that these two go together? Stay with me, stay with me. These two will be the same. Right? Maybe it'll be easier if I do it this way. Guys, do you see how the tops of all these are blue? Do you see how the bottom rights of all these are orange? Do you see how the bottom left of these will all be green? Is that better? Because they're capped, right?
Yeah.
Do we see that? I'm sorry, my triangle looks kind of gross. Now, these 3 triangles are all similar because they have all the same angles, right? This triangle in here, well, if you look, isn't orange plus green plus blue 180, right? So if I have orange and green, what color must this be? Blue, because they all have to add up to 180 and they're linear. They're all on a line, right? Green and blue, what color will this be? Orange. Blue and orange, what color will this be? Green. So all these triangles are similar. So we know from our proof way, way, way back when that if we have all these triangles being similar, right, that means that these 2 sides right here are going to be congruent, and that's going to be the midpoint. So A is the midpoint of this side. So in other words, this and this is congruent. We know that to be true. And we know that this and this will be congruent. And that this and this will be congruent. So, big triangle, guys, let me draw it out like this. If I connect up the midpoints, right? We learned this earlier. That means that this side will be parallel to this side. This side will be parallel to this side. This side will be parallel to that side. Okay? Same thing in reverse. So we get all this information, right? So, we're going to draw the perpendicular bisectors. There's the bisector of this guy. Perpendicular from there. 90 degrees, okay? So I'm going to draw 90 degrees straight up. That's 90. I'm going to draw 90 degrees straight up from here. That's 90. I'm going to draw 90 degrees from here, which if I do this right should all intersect. So right there, perpendicular bisector, that's the circumcenter, right? So all of our perpendicular bisectors intersect right here. Okay? I'm going to prove that that's also the orthocenter. Okay? If this is 90, take a look at this. If this is 90, this bit right here that I colored in black, if that's 90, this is parallel to that. So this is our transversal. Look, look, look. This is our transversal, right? And here are our 2 parallel lines. Alternate interior angles. This is 90. Are you seeing it? Two parallel lines, the blue lines. Blue lines are parallel, right?
Oh, yeah.
That's the transversal, so alternate interior. Those are 90. Green lines are parallel. So if that's 90, this is 90. Orange lines are parallel. So if that's 90, alternate interior angles, this is 90. And now if you look, I have perpendicular bisectors for all my triangle intersecting. We'll finish this up tomorrow. I'll do it again. with markers.
So whenever
okay?
you do alternate interior angles, can't you just do it again to prove that all four are the same?
I don't know what you mean by that, but maybe.
Like if you get this, the
We'll get a chance to look at it one more time. I know, it is. Again, don't write, just watch. We'll do it one more time tomorrow, and then we're done. Whew. We'll give you one more look tomorrow. I have feared orthogonals for a long time.
I don't think Miss Coulter's here today, so I might be able to come. If you want.